Okay, we're going to continue on, like I said, and hopefully wrap up this chapter, get a little bit into the next one, and then I hope we'll call it a day, I suppose. All right. So we've been talking about something chemistry like. So talk about liquids. So we're going to talk a little bit more about water, just a little bit here. Again, obviously, three-quarters of the globe is covered with water. Some of the properties we've talked about up to this point as well. Obviously, it can participate in hydrogen bonding, which is again a really strong intermolecular forces. Some of the unusual properties that we've talked about again, ice being less dense than liquid water, density does change with temperature, and we when we do have one water bonded to another, again through our hydrogen bonding, as we've discussed, the positive side of one attracted to the negative side of another. And again, that's why we have something like 100 degrees Celsius for water as its boiling point, as that's relatively a strong boiling point versus say something that's organic, which has a much, much lower sort of boiling point. Now, water molecules and ice, they do expand as we talked about. So as they sort of lose that energy, as they're going into the solid phase, and they're held together by these really strong hydrogen bonds. They really, as I mentioned earlier, don't have enough energy to get as close as they can in the liquid phase. Once again, creating these really open areas in the three-dimensional sort of structure of ice, making it again uh, more less dense, but also the tendency to expand. So if you've ever maybe threw a can of soda or something in the freezer to cool it down and forgot about it, and you come back, usually what you'll see is perhaps the can of your bottle there is, or the bottom of your can is going to start to kind of expand out. And again, it's because obviously it has nowhere to go at that point. So it's going to kind of push the can out, and now you have a wobbly can when you take it out of the freezer 2 days later. If it didn't actually pop from the pressure of that guy expanding. Now, all phases of matter, with a few exceptions, expand when heated and contracted when cold or cool down. Liquid water below 4 degrees is bloated with ice crystals. So when it warms from 0 to 4 degrees, the volume decreases, and those ice crystals do collapse and actually has a greater density. Liquid water has its greatest density around 4 degrees Celsius, which is about 1 gram per milliliter, which is typically what we associate with the density of water when we need to use it. Once again, obviously, it does change with temperature, as we saw maybe in that experiment we did, the gas experiment when you looked it up, some density of water. This is also a really good sort of characteristic of water for the sense of when water freezes, say in a lake or some type of body of water like that, it actually freezes from the top down and not from the bottom up, right? If it freezes from the bottom up, that would not be so good for the fishes and stuff maybe that live there, because that would not end well. It freezes from the top down because the warmer water is going to be more dense, so it's going to go to the bottom. The colder water is going to go to the top, where it's going to freeze and make this layer of ice up there on top, which actually will then sort of insulate the bottom liquid water from freezing there, right? Which is why if you live around lakes that just partially freeze and you go out there, you can find yourself in the lake pretty quickly, right? Because it's not a very big layer of ice there. It's just the top layer kind of freezes. Still super cold water for us if you go for a swim in that. Um, and again, that's really good for obviously people living in the ocean, like fishes, like our friend here, Melvin the fish. Right? That is Melvin the fish, right? Definitely going to show up on the next exam, so make sure you know his name, right, when you see him. Although this is really old clip art, so it does look like he is in a block of ice, but he's really not in a block of ice. He's swimming freely there. But again, like I said before, kind of the warmer water is going to go to the bottom, colder water is going to go to the top, going to create this ice layer up on top where it freezes, kind of insulating the down, and again, allowing Melvin to have a happy life here swimming, as long as nobody goes ice fishing, I suppose, and drills a hole in the ice and starts go fishing. All right, now that we talked about liquids, we're going to finish up this chapter talking a little bit about some solids and some calculations involving solids. Um, and solids are obviously very different than liquids. That is usually, again, the state of matter where everybody's usually packed in there pretty tight to one another. They lack a lot of energy, so there's not a lot of movement of molecules or atoms by each other. They're very rigid, which means it's very hard to change their shape. There's a couple types of solids. There's a crystalline solid, which is a very ordered arrangement of individual particles, things like salt, minerals, gemstones. There's also amorphous solids, which have very little order long range, but can have definite shapes like glass and organic polymers. Now, a crystal lattice, when we talk about sort of solids with long range sort of order, a crystal lattice occurs when we really cool down the particles in a liquid and release a lot of that energy. Everybody's going to really try to arrange themselves in a way where they're going to kind of maximize the attractive forces between the molecules or atoms. Remember, kind of maximizing positive and negative things being near each other and trying to minimize where we get kind of negative and negative things near each other are positive and positive things near each other. The result will usually be this crystalline solid. It usually has a crystal lattice, and there's usually a part of that repeatable pattern that is really good, which is known as a unit cell. And a unit cell is like a little snapshot of the arrangement of a solid that, because of this really repeatable sort of pattern, you could actually use that snapshot to rebuild the three-dimensional sort of structure. So, for example, if you had a three-dimensional structure really badly drawn by my picture here of this, all these circles, and you pull a unit cell out, it will allow you to recreate this sort of three-dimensional structure. Now, you may be tempted to go, all right, well, it kind of makes sense. Maybe if I just grab myself an atom or molecule here, and that's going to be my unit cell. The problem with if you grab, for example, that guy as your unit cell is, now what do I do with that? I don't have any relationship between that one and, say, an atom next to it or a molecule next to it. I have to sort of guess sort of how to arrange everybody. So when we're sort of choosing a unit cell, we probably would not want to choose a unit cell that, has no relationship to how other things are put into this structure. And maybe a better unit cell would be if I, instead of grab that, I decided, well, I'm just going to take myself a square of like here to here to here to here. And now if I pull that unit cell out, what I'll end up with is basically something that looks just like this, which means I don't have to think too much about it, because if I just attach another one next to it, it also will have all that relationship. Pop myself one up on top and put another one over here. I didn't run out of room up on top there. And now you can see that by grabbing a little piece of this guy and a little piece of this guy and a little piece of this guy and a little piece of this guy, what I get is actually the relationship of how they are to each other in that sort of just three-dimensional structure. And that's what allows me, because of this repeatable pattern, if I just continuously pile up squares there up on top, I can eventually rebuild pretty much this entire sort of structure. I, again, could not do that if I really didn't have any relationship between how that one sits with another atom. Any questions on that there? And that's what we see here. We're looking for, again, where we can see a relationship. like I did there. This one actually has a whole entire cell in the middle, our whole entire atom in the middle. And that's good because, again, if I just keep rebuilding it, I could get that entire relationship that occurs. Now, when we talk about unit cells, there's a bunch of different types of unit cells. We're not going to go super deep into it, but just a little bit about some basic cubic unit cells where everybody's basically 90 degrees. Kind of makes the math a little bit easier. So we're going to look at those type of cubic cells. And when we talk about unit cells, we sometimes talk about coordination number. And coordination number is basically how many particles are in contact with other particles. So directly touching each other, that's going to give you your coordination number. The higher the coordination number, the stronger attractive forces are holding that crystal together. And there's a lot about packing efficiency, how they kind of arrange themselves to be able to efficiently be put into a three-dimensional arrangement. So let's talk about cubic unit cells. They all have 90-degree angles. There is on each corner of that cube 1/8 of an atom. So if you have a corner, it will have 1/8 of an atom. If you have a atom on the face of the cube, it will be a half of atom. And if you have one within the edge of it, it will be 1/4 of an atom. If our volume, we're going to be looking for a volume of a cube. We're not going to really do anything too much with spheres. So to find the volume of a cube, it's equal to the length cubed. Basically, kind of like when we do density, which is kind of what we're going to do here, where you take centimeters times centimeters times centimeters. That gives you your cubic centimeters, right? Length times width times height. And that is our length cube, which gives us a volume. So ultimately, we're going to kind of use some of these calculations to figure out the density of certain things. And we're going to be looking at the density in grams per cubic centimeter. And remember that a milliliter is the same thing as a cubic centimeter. So let's talk about three different types of cubic cells. One is a simple cubic. It is sometimes abbreviated as just SC for simple cubic. And in a simple cubic cell, and we're going to look at each of these more specifically in just a second, there's basically one atom total per unit cell. So if you take out that unit cell, if you add up all the pieces that you have one complete atom, which is an important thing to know. This is a body-centered cubic cell, sometimes abbreviated as BCC. This is also has two total atoms as part of its unit cell. It has basically one atom at each of, for the total of all the corners, and stuck in the middle, as we'll look at shortly, there's one entire intact atom kind of stuck in the middle. And there's also face-centered, which is sometimes abbreviated as FCC for face-centered. It has four total atoms. It has one atom from the corners, and on each face of the cube, there's a half atom. And in that case, there's six faces, and half of six is three. Three plus the corner guy there is going to give us our four atoms. Each of the cell lengths are a little bit different of a calculation, and we're going to go through those as well and sort of see what we're going to do in terms of our calculation. So let's start with the simple cubic cell. And in the simple cubic cell, as I said, you basically have 1/8 of an atom in each corner. So there's 8 corners. 8 times 1/8 is one entire atom. So you'll have one entire atom in a simple cubic unit cell. They're basically made up as 1/8 of an atom in each of the corners of the cell. The length of each of these cells is 2 times the radius, and that is the radius. And it's basically 2 times the radius will give you the length. So the first thing you should know, again, simple cubic has one atom, and to calculate the length, the edge length, it is 2 times the radius. And there you can see, again, we basically have 1, 2, 3, 4, 5, 6, 7, 8 corners. Each one has an eighth of an atom, giving us that one total atom that's happening. And that's what you can see here. Here's our eighth of an atom in each of those corners, basically. Now, body-centered cubic is BCC. And like I said before, this guy will have two total atoms. So this guy here will have two total atoms. It has an eighth of an atom in each for the total of all the corners. And it has one whole atom sitting right there, dead center in the middle of the cube. So one complete atom sitting in the middle of the cube for our two atoms. To calculate the length, it is 4 divided by the square root of 3. And that should be R, should be there somewhere. Where we go? I feel like it's missing my R there. Should be, where we go? Yeah, 4R up on top. That's what I thought. So this should be 4 times the radius divided by the square root of 3 to calculate the length of it. There it was. It's hiding right there. And again, you can see here, each of these sort of wedges is an eighth of an atom. And right there, dead in the center, is a whole atom kind of wedged in between all the corners. And that's what's going to give us our two atoms for this particular one. And lastly, here we have a face-centered cubic cell, which is sometimes abbreviated FCC. This again has an eighth of an atom at each of the corners. There is a half atom on each of the faces. And again, there's 6 faces, which gives you 3 atoms. And there are 8 corners, which gives you 1 atom. So that gives you a grand total of 4 atoms for a face-centered cubic cell. To calculate the length of this type, it is 2 times the radius times the square root of 2 in this case. So simple cubic, 1 atom total. Body-centered, 2 atoms. Face-centered, 4 atoms are going to be important to know. Obviously, the length of the edge as well is a good thing to know. All right, and there you can kind of see the half atom there on each of the face, kind of cut in half as you take it out. And again, our corner eighth of an atom happening there. All right, so let's go through a calculation here to kind of see how we're going to kind of use this information to help us calculate what we're looking for. In this particular case, we are looking for the density of aluminum if it crystallizes in a face-centered cubic cell, and it has a radius of 143 picometers. So the first important information here is face-centered, and that was the one we just saw there on the previous slide. That is the one that has basically 4 atoms in this case. So this guy's got 4 atoms. And we are looking for the density here in grams per cubic centimeter, essentially. So we are looking for basically our grams per cubic centimeter. And we have a radius that is 143 picometers. So we are looking for our density here. So there's a couple of things that we basically need to find to figure out the density. Is pretty straightforward. We need the grams and we need the cubic centimeters. So we're going to start with the grams part. And the grams part is actually going to come from the atoms. So since there are 4 atoms in this cubic cell, I could use my friend that we haven't used for a bit, Mr. Avogadro, and his number, 6.022 times 10 to the 23 atoms, is a mole of aluminum, right? And if I do that at this point, the atoms will cancel. I will be left with moles, but I don't need moles for the top of my density. I need grams. So I could go to the periodic table and I could grab myself the molar mass of aluminum, which I hope is 2698 grams per mole of aluminum. That's going to cancel out the moles. And that is going to give me the grams part of my density that I need. So that again is why it's important to know it's face-centered. It has 4 atoms. If this was simple cubic, it would only have 1 atom, right? And the calculation would be a little bit different. So we would do 4 times 2698 divided by Avogadro's number, remembering to use our exponent button. That is going to get us here 1.792 times 10 to the minus 22 grams. I am halfway home to my density here. I have the grams part of it. So the grams part when you're doing density for these things will always come from how many atoms are present in that unit cell. For our purposes, is either going to be 1, 2, or 4 atoms, basically. Any questions on that so far? All right, so the bottom part, which is a cubic centimeter, is a volume. So we do need to get the volume. So also important here is, again, this is face-centered, which means if we go back and take a look, right, we can see that our face-centered, to calculate the length of the edge, is equal to 2 times the radius times the square root of 2. So that is what we're going to use here. We're going to use our 2 times the radius times the square root of 2 is equal to our length. Now, what you might want to do is what I'm going to do, which is our radius at this point is in units of picometers, right? Our volume, though, is in units of basically centimeters cubed. At some point, you're going to need to convert to centimeters. So you might just want to do it up front and go from picometers to centimeters. That way you could just do the calculation and everything will be in the right units. So that is what I'm going to do. I'm going to convert my radius from 143 picometers. Pico is, I believe, 10 to the minus 12, I hope. So that is going to give me 1 picometer is 10 to the minus 12 meters. And in 1 meter, there is 100 centimeters, right? So again, I'm just really converting from picometers to centimeters. That's going to be 143 times 10 to the minus 12 times 100. Going to give me a lot of zeros that I don't want to count right now. So that's going to give me 1.43 times 10 to the minus 8 centimeters. So again, the reason I did that is just to get it in the right unit at the end. Now that I have the radius in centimeters, I can use my formula for face-centered and take 2 times my radius, 1.43 times 10 to the minus 8 centimeters, times basically the square root of 2. And that's going to get me here. Looks like 4.0447 times 10 to the minus 8 centimeters. First off, any question on that calculation there? So this you need to remember, though, is not a volume. This is just the length, right? And what we know is in a cube, the volume is equal to the length cubed. So basically what I need to do is take my number I just got, my 4.0447 times 10 to the minus 8 centimeters, and I'm going to cube it to turn it into a volume. And if I do that, I will end up with, I believe, 6.617 times 10 to the minus 23 cubic centimeters, which is a volume. And dare I say, that is the bottom part that I need for my density. So now I have my grams for my atoms. I have really my volume from my radius of this guy. So now to figure out my density, all I have to do is pop those numbers together. We're going to take my mass, which is 1.792 times 10 to the minus 22 grams, divided by my volume of 6.617 times 10 to the minus 23 cubic centimeters. And if I do that, that's going to get me 2.71 grams per cubic centimeters would be the density here of my aluminum. Any questions on that there? So basically, we're going to get our grams from atoms, going to use the radius basically to get our volume, put them together there, basically to calculate the density. Some crazily weird numbers that comes out to just like a normal number at the end. Yeah. Any questions on it? All right, let's take a look at maybe another one here. That's the same one. Uh, all right. Why don't you try this one? Why don't you try rubidium? It crystallizes in a body-centered. It has a radius of 247.5 picometers. I would tell you what that says in terms of the molar mass, but I'm not sure. Right over there. Maybe it's on this page. We'll maybe just borrow that there. Maybe 8547 looks like. I'll borrow there. 8547 grams per mole is rubidium's molar mass. All right, just take a few moments there and calculate it up. See what you come up with. We're looking for our density in grams per cubic centimeters. Okay, let's take a look. So again, the key here on this one, body centered. That should tell us we have two atoms. So this is the one that has one atom from the corners and one stuck kind of right in the middle of the center of it. It also has a 4r square root of 3 for the length as well. So here we're going to look for basically both of these things. So I'm just going to kind of approach it the same way. I'm going to start with the grams part. That's going to come from my atoms. So we'll go with our two atoms here. Use our Avogadro's number. Going to give me moles of Rb. And again, using the molar mass from the periodic table, 8547 grams per mole. Moles will cancel, atoms will cancel. And that's going to leave us here 2 times 8547 divided by 6.022 to the 23. 2.839 times 10 to the minus 22 grams. That again is the top part here, what I need. Bottom part is going to come from obviously the radius that was given to us. Just like on the previous problem there, I'm going to put it into centimeters, so everything's in the right units that I need. Again, 1 picometer is 10 to the minus 12 meters, and there's 100 centimeters in 1 meter. So those cancel, and that's going to turn me into my centimeters that I need. Looks like 2.475 times 10 to the minus 8 centimeters. Remember, again, this is not the length or anything. We haven't done it yet. So we're going to use our specific one here for body centered, which is 4 times the radius divided by the square root of 3. That's going to give me 4 times 2.475 times 10 to the minus 8 centimeters divided by the square root of 3. So if I do that, it looks like I end up with 5.716 times 10 to the minus 8 centimeters. Remember, this again is just a length, so we got to turn it into a volume by cubing it. So we'll take our volume, which is our length cubed. So that would be that guy there cubed. And we will end up with 1.867 times 10 to the minus 22 cubic centimeters, which is the bottom part there that we need. So now to calculate our density, we're going to put our both numbers in there and see where we end up. 2.839 times 10 to the minus 22 grams divided by 1.867 times 10 to the minus 22 cubic centimeters. That's going to get us here. Looks like 1.520, we'll call it grams per cubic centimeter in this case. Any question on that calculation there? All right, so we're just going to stay with the basic sort of cubic unit cells, simple cubic, body-centered, are face-centered, and probably something to do with density calculation is what we're going to kind of roll with. You will be provided the formulas for the length of the cells, but you do need to know how many atoms each one has, so that won't be provided, but perhaps somewhere on the paper there will be those guys provided for you, okay? But you do need to know, again, simple cubic has 1, 2 for body-centered, and 4 for our face-centered one. Any questions on that there? All right, that is going to wrap it, I think, for this chapter. Nothing else is that important, I think, here. All right, we're not going to worry about that. All right, so we're going to go off to chapter 10 here next. The good news is there's only chapter 11 after this one, right? So we got to be to the end. We got like 4 days to go, so we got to be to the end soon. All right, so in this chapter, chapter 10, we're going to talk about a little bit about solutions and some properties of solutions. There is kind of the middle of this chapter that we actually kind of already just talked about when we were doing kind of like molarity, stoichiometry, so things like molarity, percent mass, mole fraction, molality. So there's all those sort of calculations that we did kind of previously. So I'm just going to kind of point them out. I'm probably not going to go through the examples, obviously, again, or anything like that. You hopefully should still remember how to do all those things. But this is sort of the chapter from where that stuff came from. All right, but let's talk a little bit about liquids and liquids. So when we're talking about two liquids that basically mix together, they are said to be miscible. And miscible is sort of used as a term for solubility when we're talking about two liquids that mix. So usually when we talk about solubility, a lot of times we talk about it in the sense of solid dissolving in a liquid, it's soluble in each other. When we talk about two liquids, if it's miscible, it basically means it's soluble and they will mix. And what that means is if you put those two together, it essentially will just look like one liquid's in there. You won't see any layers or anything like that happening. Everything should mix together. And again, solutions that mix really well together are things that can interact the same way they interact with themselves. So if you take something like ethanol, which is this guy right here. So this is ethanol. And ethanol has this OH bond on it, which is negative and positive and polar. And that works really well when it hooks up with water, which pretty much has the exact same bonds. They both could do their favorite thing ever, which is hydrogen bond with each other. So water usually hydrogen bonds with water. Ethanol can hydrogen bond with ethanol. So when those two come together, because they both normally use hydrogen bonding with themselves, they're going to have no problem mixing with each other. They're going to be perfectly fine and happy, and they're going to be quite soluble in each other. When we have two liquids that really do not mix with each other, they're really insoluble. And sometimes when we talk about liquids, we talk about it as being immiscible. And if you mix those type of liquids together, you will see some layering happening because the two different liquids are not going to mix. They're going to really separate out into different layers within, say, the test tube. So if you take something like carbon tetrachloride and you want to mix that with water, carbon tetrachloride, as you remember for a throwback conversation of polarity, that is a symmetrical geometry where everything on the outside is the same. So even though it has polar bonds, perhaps that is a non-polar molecule because of it. And it's going to be rolling with dispersion forces, right? While our friend water here is going to be rolling with hydrogen bonding, and those are very, very different types of intermolecular forces, not going to happen. They're not going to stay mixed. They're going to definitely separate out into different layers. Even though water can kind of do a little dispersion forces, there's no way to maintain that interaction together. So eventually they will separate out from one another and we will get this different layers that occur. And that brings up a really important sort of idea about solubility is the idea of like dissolves like. So things that use similar intermolecular forces will be definitely soluble in each other. So what that means is essentially you are good to go if you got a polar guy and a polar guy coming together. They're both going to use some type of dipole-dipole interaction. They're going to be fine. If you have an ionic compound and a polar, they're going to use some type of ion dipole, also going to be good to go. And if you have a nonpolar guy and a nonpolar guy, they're also going to mix together because they're both using dispersion forces, so they're using the same type of interaction. You're only going to run into some problems when you try to cross over a polar and a nonpolar. You're not going to get it to work. And again, because much like this example here, they're using very different types of intermolecular forces that cannot really work well together, and they're not going to mix pretty well. Any questions on that there? As you can see here, we start to see some different layering as they do not mix with one another in that test tube. So when we talk about things being soluble in water, ionic compounds are definitely soluble in water. They do that ion dipole interaction. And that's all good. That's basically like we talked about many times of how something dissolves. Again, like the negative side of water, which is the oxygen, is going to surround like the positive ion, while the negative ion you're trying to dissolve will get surrounded by the positive side of water, which is the hydrogen part of it. Um, there are also non-ionic compounds which are again soluble in water. Sugar is an example, ethanol, as we just talked about. And what they both have in common, again, is they do contain a polar group like that OH. Sugar, although it is a larger molecule, is littered with OH groups all over it. And everywhere there's an OH group, it gives water a chance to interact with it, and it makes it quite soluble. As we know, sugar will dissolve in water. Ethanol will do that hydrogen bonding, as we just talked about. Same thing here with like methanol, which is what this guy is. That's methanol. Also has this polar OH group on it. Going to work perfectly great with water to hydrogen bond. Is going to be very, very soluble. Now, although something does have a polar group like ethanol or methanol that have this OH group at the end of it, if you were to build out like usually 5 or more carbon part of it, there does come a point where if that back part is all carbons and these are all hydrogens with them as well, I won't draw them all in, but there's hydrogens all around all those guys. That non-polar part, which is in the box, if that part gets too big, even though you got this polar part over here, it is not going to be soluble in water. And usually around 5 carbons or more is where that kind of comes into play. And that is because something that occurs here, which is known as steric hindrance. That's a fancy way of saying that part is just way too big and it gets in the way of this guy being able to interact with water. So it kind of gets in the way of it and it prevents it from interacting with water really well. And it decreases the solubility to like nothing at that point. So there is a lot of factors that sometimes come in play whether or not something will be soluble in water, and that's one of them. Um, Remember, ultimately, if you want to dissolve something in water, you have to replace water and water interactions with similar type of interactions and things that aren't giant, right? So you get something giant molecule in there, it's not going to work well with water molecules because they're very small to begin with. And again, here's ethanol bonding. And as I mentioned before, oil will not be soluble in water because oil is nothing more than just a super long chain of carbons and hydrogens attached to each other. and that is nonpolar all day. So this is all nonpolar. And once again, it runs into two problems. It wants to use dispersion forces. Water wants to use hydrogen bonding, which is the first problem. The second problem is they're usually really big. And again, that's just going to get too big to interact well with water. Will it be able to work a little bit? Maybe, but they will separate it out. That's why if you ever seen an oil spill, right? Oil floats on top of the ocean there as it's been spilled, and that's because they will separate out from one another. Um, it's like again, you could park a car into a garage and it will fit. And maybe you could get like a semi truck or part of the semi truck into the garage, but it's just not going to fit right? So you try to pull a semi truck into a normal garage, it's not going to fit in there. Maybe you could get a little interaction into there, but it's just not going to be right. And that's sort of what happens here. And again, that's the idea behind our like dissolves like. We do get different types of interactions that do occur. And one type of interaction that can occur is what is known as a hydrophilic interaction. Hydrophilic means it's water loving. So that's any type of polar region on a molecule is going to be very hydrophilic. It's going to work well with water. It's going to interact with water, like the OH group in ethanol. That's a hydrophilic region. The one that we talked about with soap earlier that has this part of it at the end, that polar part of soap is hydrophilic. The back part of soap, which is nonpolar, is hydrophobic, which means it does not like water. So hydrophobic areas do not like water, and that's usually where you have nonpolar parts of molecules that don't work. A lot of organic compounds like soap and other type of things, they typically will have kind of both of those. A lot of them will have both regions like that. They'll have like a hydrophilic part that's going to work well with water and interact well, and they'll have a nonpolar part that's not going to interact very much or very well with, say, water. Here's our kind of oil component separating out from water. And by the way, the water layer is usually the bottom, the oil or organic layer is the top. And here, though, if we mix octane, which is nonpolar, with carbon tetrachloride, which is nonpolar, you can see it mixes really well because they're both using dispersion forces. It all looks like one layer. It doesn't look like there's two different things, obviously, in that beaker. Now, when one substance does dissolve in another, it is said to be soluble. So salt is soluble in water. When one substance doesn't dissolve in another, it is insoluble in water. So oil is insoluble in water. There is usually a limit to the solubility of one substance in another. Gases are typically always soluble in each other. So if you just think about gases in a container, they are technically flying around, which means they are constantly mixing with each other, right? So just by the nature of how they're flying around, they're constantly mixing and going to be soluble in each other. Some liquids will be mutually soluble in each other. So as we just talked about, that's your polar and polar guys going to be good. Your nonpolar and nonpolar guys are going to be good with each other. Again, if you cross over polar, nonpolar, not going to work well together. Uh, in terms of the solubility of a solute in a solvent, a reminder that a solution is made up of those two things. A solution is the aqueous symbol, and it is the solute, which is the smaller part of the solution, and the solvent, which is the larger part of the solution. So again, if you had a sodium chloride solution, sodium chloride would be your solute, and water most likely would be your solvent. Usually the name of the solution again is the solute that's dissolved in there. So temperature plays a big role in solubility. At higher temperatures, you could usually get a larger solubility of a solid in a liquid. So if you usually have trouble dissolving a solid, sometimes they'll tell you to warm it up a little bit, and that will allow you to get more of it to dissolve. And when you do so, why that happens is obviously as you increase the temperature and warm it up, you're adding more energy. That's going to allow things to start to move and start to dissolve in one another. At a lower temperature, you have a larger solubility of a gas in a liquid. So if you have a liquid and a gas molecule in it, at a lower temperature, we know the gas molecule is flying around slower, which means dramatically drawn here, it is going to stay in the liquid part for a much longer period of time because it's moving slower before it decides perhaps to exit. Obviously, the opposite would be true at a higher temperature. It's probably going to pop right out. That is what we were just talking about earlier. When you hit the beaker of water with the Bunsen burner right away, you see all those little bubbles come out. That is an increase in temperature causing the solubility of the CO2 that's in there to pop out of the liquid really quickly. And that's all those like little really bubbles you see at the very beginning when you heat it. The solubility of a gas does depend on the pressure. So we know based on higher pressure, that should probably mean our volume should be low. And if our volume is low, we definitely have a lot of gas molecules near each other. So they're going to be constantly mixing because they don't got very far to go, right, to fly around in. It's a very small sort of area. Now, when we talk about solutions, there are different ways that we classify solutions. As I mentioned, there is a limit to how much you could get to dissolve of a solute in a solvent. What happens if you add too much solute to a solvent? You hit what is sometimes referred to as the saturation point, and you make a saturated solution. And a saturated solution is a solution where you have basically hit at that temperature the maximum amount of solid you could get to dissolve in that solvent, basically. So if you add more to it, at this point, you're good. You will have a solution. And at that saturated solution or saturation point, if you decide you want to dissolve more, it's not going to dissolve. It's just going to kind of pile up there on the bottom. No more will dissolve at that point. You know, you could dissolve, for example, right, a packet of sugar, maybe get the Costco size sugar and put it in a glass. At some point, that sugar is not going to dissolve anymore, right? You just have too much to do it. The opposite there is an unsaturated solution. In an unsaturated solution, you have not reached that point yet. So you can continue to dissolve solute until you hit a saturated solution. So in an unsaturated solution, you haven't hit the maximum to dissolve. At that point, you can continue to dissolve. It will continue to dissolve until you hit a saturated solution. And at that point, obviously, it will not dissolve anymore. A third type of solution is a very unstable solution. That is a supersaturated solution. In a supersaturated solution, you have way too much solid dissolved in that solvent or too much solute dissolved in it. It makes a really unstable solution. How do you make typically a supersaturated solution? Well, you take a solution, some water, and you heat it up. And as you're heating it up, you're going to dissolve a lot of solid in there because the temperature of that solvent has now increased. And that's going to allow you to dissolve a lot more solid in there than you normally could at like room temperature. And by doing so, you're going to be able to get a solution that has now a lot of solute dissolved because we rose the temperature. And when you do that, you then kill the heat and you basically just let that test tube or beaker cool back down to like room temperature. You try not to touch it too much. You just let it chill out. It will cool back down. When it cools back down, you now have a solution that is still a liquid, but you now have way too much dissolved for it at the cooler temperature. So you heated it up to get all that solid to dissolve. You cooled it back down. It's like, whoa, it's already dissolved too late. I got it all dissolved. So now you have too much dissolved in there. It is so unstable that if you just like knock it too hard, it will cause the solid to come out of the liquid. You could also force it to do that by simply just taking a speck like that big of whatever you dissolved in it, and you decide, I'm just going to drop it in there. If you drop that in there, it's going to go, whoa, too much dissolved. All the solid is going to come out of the solution, and it will go from a liquid solution to a rock hard solution in a matter of seconds, and all of it will come out. And that's because at the lower temperature, you already have way too much dissolved in there it shouldn't be, and you just kind of tilted it over the edge by putting that little bit in there. But it is really unstable. In fact, I just did this last week and I demonstrated that I don't even need to add the crystal. I just took the flask and did this. And then a second later, I looked back and it was rock hard from a liquid. And, so it's a cool experiment. They used to let students do it, but they used to have students put their thermometers in the test tubes and like cool it back down and then do the super saturated. Then they end up with like lollipops with thermometers that have frozen in there. People are like, how do I get it out? Crack it. No, that's what too many people did that. So they're like, no, we don't need to do that anymore. And that's that experiment I was just talking about. This is a supersaturated solution of sodium acetate. You can't even really see it, but he's dropping like one little speck of sodium acetate. And you could kind of see it goes from liquid, and that's all solid starting to form. And then as it gets more solid, coming out of solution, more solid. And at this point, it's going to be just a rock hard solid at that point. And it's a very unstable type solution. Any questions on that there? All right, let's talk a little about pressure and the solubility of gases. When we have an external pressure, it does have an effect on the solubility of gases, as we talked about. You could actually calculate the solubility of a gas, and it is proportional to the pressure of a gas. This is what is known as Henry's law, the soda pop calculation. It is C is equal to K times P. This is really the molar solubility. That's a fancy way of saying molarity, basically. That is Henry's law constant. That is a constant value you would look up in a table based on the gas you're dealing with, and that is the pressure in this case. And sometimes people will use S instead of C for molar solubility as well. And this is a Henry's law constant table. You can see different gases have different constants that you would look up. This is basically our soda pop situation, right? Before you pop the can, your soda is under a lot of pressure, right? And it has all of our CO2 gas molecules dissolved in the liquid part of the can because it's under a very high pressure at that point, right? About maybe 4 times normal pressure it's under there. And that's going to keep all that CO2 in here. But you're thirsty, so you pop the top. And perhaps if you notice, sometimes you start to see some fizzing coming out of the top, right? You just did two things. You released the pressure, which is going to make this gas less soluble in there. So it's going to come out. And it also has now an escape route, right, to get out of the can. And that is what you're seeing when it starts to fizz out of the can. What happens if you leave your can open for a while and you go back and taste it? It tastes very flat, right? And that's because you gave that CO2 an escape route, and air is going to push it away, and none of that gas is coming back in, right? So you're basically just going to be left with pretty much just some syrupy water, right? And or whatever your Coke is in that case, maybe a couple few CO2 in there. It's not going to be obviously as fresh tasting as before. So we could use something like Henry's law here to calculate what pressure is needed to keep a soda at a concentration, a CO2 concentration of 0.12 at 25 degrees. So we could use Henry's law, which is whichever one you want to use, the C or the K or the S times our pressure. We obviously would go to that table and look up the Henry's law constant for CO2, which is our gas here of choice. And we want to keep it at 0.12 molar. We have our Henry's law constant here, 3.4 times 10 to the minus 2 molarity over atmospheres, which is a pressure, times our pressure. So if we just divide that to the other side there, that will give us the pressure that we need to kind of keep our CO2 concentration where we want it for our soda can. And we're going to end up with a pressure of about 3.53 atmospheres, right? So normal pressure is about 1 atmosphere. So your soda can is about 3 times or so the pressure needed to keep that CO2 in the actual can of a liquid part to keep it fresh. Any questions on that there? That's hopefully what they got. I hope. There we go. All right. All right, so this is sort of the review part of the chapter. Again, just to talk about some of these concentration units and review them really quickly. We're not going to do any examples because obviously we went through a number of them in the previous lectures. But we will use some of these sort of calculations for the last part of the chapter, which is colligative properties of solutions. Obviously, we talked about this guy here, which is our percent mass to mass. And remember that when we use this one, the important part is really the bottom part, is the mass of the solute divided by the mass of the solution times 100%. But it is the mass of the solution is important to remember on this one. You want to make sure that you do get both of those things, the solute and the solvent, as they are commonly given to you separately. So you want to definitely make sure that you don't just get one versus the other. Again, I'm not going to do that calculation. We did it previously in the previous chapter, along with that one as well. Molality is also a really important calculation for colligative properties. It's in a number of the formulas that you will need to use in those guys. And remember that molality is different than molarity. So molality, again, is abbreviated with a little m for molality, and that is the moles of solute divided by kilograms of solvent. So this is basically moles over kilograms is the molality. Once again, as we'll see here in a second, as hopefully you know, molarity is moles per liter. And again, a reminder that if you kind of want to go between these two, density is usually the thing that kind of ties those guys together. You can use the density to kind of go back and forth between molarity and molality. But molality definitely shows up in a lot of calculations involving colligative properties of solution that we're going to talk about, which was also sort of part of the lab that was scheduled for today, which is boiling points and elevation, freezing point depression. Mole fraction, again, is another thing that does pop up in a number of the calculations involving solutions. And a reminder that basically we're just going to take the moles of what you're interested in and divide it by the total moles. It really is like a percentage without the percent part of it. So we don't multiply by 100 or anything like that. And again, if you have 4 different moles, you take each one individually divided by the total moles, and that will give you it. The total there of the mole fraction should add up to 1, which is essentially 100%. So we're not going to do that example that we did earlier. Molarity, obviously, hopefully you should still know, which is what we just talked about. Obviously, our moles per liter. That also pops up in these colligative property type of calculations. So speaking of colligative properties, these are where we're going to kind of see these concentration calculations come into play. And colligative properties really means about how many particles are in the solution. And depending on how many particles are in the solution, it can have a really big effect on things like freezing points, boiling points, these sort of physical properties, because there's a lot of things dissolved in it, osmotic pressure. So we're going to talk about vapor pressure as well. We're going to talk about the effect of all those things next time. Yes, we're going to talk about it next time. All right. Any questions on any of that?